Hi everyone, my name is Yifan. I'm currently a PhD student majoring in computer science at University of Illinois in Urbana-Champaign. I mainly work in the area of robotics, especially in planning and that involves context. I am especially happy to present my work to you guys today because I once worked under Isuru when I was an undergrad at Vanderbilt University. The topic of my talk today is data-driven simulation for deformable contacts. I'd like to start by talking about why simulation is actually important for robotics. First of all, simulation allows roboticists to efficiently develop and iterate mechanisms controlling algorithms before actually involving hardware, which could be very costly and sometimes even dangerous. Compared to real-world testing, simulation also has the advantage of offering the entire state of the system. This is very useful because in some cases, in the real world, doing state estimation by itself is a very challenging problem. In addition to using the simulation as an sort of external testbed for algorithms, physics engines are also at the core of many planning and controlling algorithms, for example, reinforcement learning and trajectory optimization problems. So the goal of my research is to build better simulators and use these better simulators in motion planners, and hopefully we can can get better motion plans. So for today's talk, I will start by discussing semi-empirical simulation, which is the approach I took for the two projects I've worked on. Then I will talk about how I built these semi-empirical simulators for rigid objects interacting with granular media such as sand and deformable objects. Finally, I will talk briefly about my current research directions. The overall idea of semi-empirical simulation is to combine human knowledge, such as physics, with data and learning. When building simulators, the classic way is modeling, such as we use Newtonian mechanics and such. However, there arise situations where the physics is simply just too complicated for us to understand, or using these laws would be way too computationally expensive. Um, on the other end, we have a pure data learning. Um, however, although given enough data and an expressive learner, we can hopefully learn a pretty good model. However, this process requires a large amount of data and for complicated systems, and this amount of data usually is too costly and sometimes even impossible for robotics applications. So in the middle ground, we can have kind of have the semi-empirical simulations where we use well understood laws of physics to combine with data that abstract away a lot of the complex part. So model-based simulators are very widely used in the field of robotics. For example, in the picture shown on the left, we have PyBullet, which basically uses rigid body dynamics combined with rigid contacts and Coulomb friction. It also supports limited deformable object simulations as well. This is actually really fast, and the physics behind it is pretty well understood, except for maybe collisions. Collision is still a phenomenon that people are looking into. On the right, we have a simulator called Chrono. It is a discrete element simulator that simulates rigid and deformable objects interacting with a large amount of small particles. This type of simulation is very computationally expensive. The scene shown in the picture is 1.5 second of it is reported to take about 2 days or so using using a computer. There has also been work that uses data only to learn planar push-in and rigid body dynamics. These problems are limited to low dimensions. Semi-empirical simulation is not a new idea, and it's been around for a while. The Wong et al. Has built a model of cloth using a collection of nodes and whose interaction forces between these nodes are learned using data. The similar idea and approach is applied to the learning how soft issues react to external forces. In my first project, my motivation is the simulation of robot traversing granular terrain. In this project, when we talk about granular media, we are talking about dry spherical particles that are relatively small, and sand and pebbles fall into these categories. The behavior of granular media interacting with rigid bodies is quite complex. The most dominant one is what's called a stick slip, just like analogous to Coulomb friction. We also have high-speed inertial effects, jamming, force fluctuations, elastic deformation, compaction, and we also have the memory effects, meaning that when we then we disturb the sand, the shape would change. However, in this project, we make the assumption that the main thing contributing to the force is the stick slip and ignore all the other effects for now. Here is an overview of our method. So the offline learning part, we collect data in real world experiments, and then using these data, we learn a contact model. During the online simulation part, we combine rigid body dynamics and these learned contact models and put them into an optimization-based solver. On the right is the robot that's going to be used throughout the project. It's a quadruped with 28 degrees of freedom. Its name is Robo Simian. It was built by JPL. So during data acquisition, we basically move the robot ankle through sand and pebbles a few hundred times, showing the video here, and while recording force and data. So we basically get the different force and torque data when we move in different directions in the sand, and when the ankle is placed at different angles and depth. Next, we are going to talk about learning. Since we assume the stick slip behavior of the granular media, when the ankle is submerged into the sand at a certain depth and angle, there is a feasible wrench space. Which means that when an external force is applied to the ankle that can be resisted by this feasible wrench space, the ankle will stick and stay in place. However, when the external force exceeds what the feasible wrench space can resist, the ankle starts slipping. We note that this feasible wrench space is dependent on how deep and the ankle is submerged in the sand or pebbles, and it also changes when the orientation changes. So the goal of this, during learning is that when we given the depth and angle of the ankle, we want to output this wrench space. However, during data acquisition, we're only able to acquire a discrete set of wrenches on the boundary of the wrench space at a discrete set of depths and angle. However, we found out that in practice, with granular media, with these dry granular media, the wrench space has very good convexity, which basically means that if we have some points sampled on the boundary of this range space, we can then take the convex hull of these and build a convex range space. Learning learning these range space turns out to be a pretty simple regression problem, and various regressors would give similar performance. In our paper, we used radial basis function interpolation throughout. Here is a video of the long contact range spaces and how it changes when the depth and angle of the ankle changes. You can see that as the ankle gets deeper and deeper, the range space grows, and when it changes its orientation, the range space changes orientation as well. Note that we are plotting the 2D projection of the range space. So I forgot to mention that throughout this project, we are assuming a 2D simulation, and we will work on a 3D simulation as future work. Next, we are going to talk about online simulation. During online simulation, we use what's called the maximum dissipation principle, which says that frictional forces should always maximize the dissipation of the system energy. We combine our learned contact models with rigid body dynamics to simulate an arbitrary number of contacts. Each simulation frame involves solving an optimization problem. In the objective function, we have the kinetic energy of the system in the next simulation frame. X being the robot state, torque is the joint torques, and WC are the ground contact wrenches. We also have the kinematic constraints for the robot joints, links. Then we have an N learned wrench spaces at the N contacts. These wrench spaces are computed first by running a collision detector, which computes the depth and angle of the ankles in the sand, and then by querying the learned contact models, we get these half space representations of the convex wrench spaces. Note that this opposition problem is convex and with the linear constraints, which means that we can solve this problem efficiently in polynomial time. Show some simulation videos. At the time of the publication, we can run these kind of simulations at 10 Hz in MATLAB. Now we can do it at 100 Hz in Python. I would apologize for the poor quality of the videos. This is made like 2 years ago, and I haven't remade these videos, but we are able to make videos like using the model shown on the left. So on the top left, we have a robot pushing its ankle forward. Note that the ankle on the left is submerged into sand more deeply. That's why when you push the front leg forward, the leg on the behind stays in place while the other slips. The video on the top right is basically a video of the robot trotting on the sand. Note how the ground reaction forces change when this happens. On the bottom, we have the robot sliding on a slope made out of pebbles or sand. The pebbles are able to resist more force, and that's the reason why the robot ankle tends to submerge more into the sand surface. Next, we move on to the second project of modeling deformable objects. The motivation behind it is that we want to plan motions in deformable environments. So humans are very good at building these kind of interaction models with different objects. And we only needed really a few touches with a different object to predict how much force we're going to experience when we interact with it. And we kind of want to give a robot the same kind of capability. Building these types of models that involves forces and stiffness is quite challenging. we have very noisy sensor data in the real world. Some of the objects even have a very fuzzy boundaries, like a toy with a lot of fur. Also, these kind of 3D mesh models requires a very significant amount of tuning. In addition to these challenges, we also have that a lot of these objects do not have uniform stiffness across its surface, and it makes building these models even more challenging. Here is an overview of our method. We start by having a robot arm collecting interaction data with a deformable object. Then from these data, we learn a point interaction model, meaning that we can predict how the objects would resist a point poking at it. Then during simulation, we combine the point model with an analytical solver to solve for the contact range at an arbitrary contact. During data collection, we use an UR5 arm combined with an RGB camera and a point probe. We would take a picture of the object, a 3D picture, and poke at a few random points on the object in the normal direction, calculated using the point cloud. The bottom left is a plot of the force displacement curve that we collected on one of these objects. You can see that the sensor data is a little bit noisy, and it also actually has bias. If the visual model is completely correct, then we'd expect the force to start rising when the displacement is at 0. But now you look at this graph, you have the force start to increase at -2 millimeters, which means that our visual model is biased. And this is actually quite normal because there would be these cameras have a bias in themselves, and the calibration also involves a little bit of bias. The objects that we use throughout this project are the 5 shown here. They all have very different stiffness properties across their surfaces. During point model learning, we would like to build a visual tactile model, meaning that we want both the point cloud of the object and also the learned force response map. The model that we want to acquire has the input of the position of where you're poking at in the object, and also how deep you're poking at it in the normal direction. And the output would be the force magnitudes. With the recent advances of machine learning, instead of picking some learning algorithm that's actually able to outperform others on this particular problem, we just rely on what's called the AutoML, which basically uses Bayesian optimization to tune hyperparameters and build an ensemble of different types of regressors. We also tried including color and curvature information as the input of the model, but it does not seem to improve the performance. We are able to learn a reasonable point model on 30 seconds with 10 pokes of data. On the right, we have our learned model predicting forces on the lamb. The forces are shown, the colors show the forces predicted at 0.5 millimeters of penetration on the lamb. You can see that as number of points increase, we are able to build a better model, more refined model. Looking at the picture at the bottom, we can see that the red parts are where the bony part of the lamb is, and the blue part is where the flesh is, and that's why it's softer. when we do simulations to bridge the gap between the point model and an arbitrary contact patch, we first look at the Hertzian contact theory, which is a really old and classic theory. Shown on the picture on the right, the contact theory basically says that on a deformable object, when you push one point down, all the neighboring points would move along with it. And these relative displacements between these points can be described by a function. Basically, it's basically 1 over r being how far these points are apart on the original surface. And the shape of this deformation is controlled by this constant c here. We make an important observation in this case, which is that the displacement of each point is a combination of external force and also the neighboring points dragging it down. Using this observation, we define two concepts. One is called the actual displacement, which means the amount of displacement that's actually contributing to force. And we also define what's called the nominal displacement, meaning the displacement you see when the object is deformed. This actual and nominal displacement can be formulated as an LCP problem, meaning a linear complementarity problem. This problem basically says that the every nominal displacement is a combination of the actual displacement and also the displacement from caused by neighboring points. We have complementarity because when a component of W is, for example, W1 is not 0, we have the nominal displacement or the actual displacement be 0. One example of this point is the blue point on the right in the picture. So these blue points would actually contribute 0 amount of forces to the original object, and its displacement is completely a result of the neighboring points. We solve this LCP by iteratively remove these points, and in the end, we have a defined linear system, and we can solve for the actual displacement directly. Summing up these forces at a contact patch by querying the learned point model, we can get the contact range at this contact. Here we show some results for our simulator. We use line and cylinder probes throughout the project for testing and comparison purposes. On the right are pictures of these line and cylinder probes poking at the 5 different objects. Note that how close and how accurate the simulation is depends on the shape parameter C mentioned in the previous slides. And right now we do this manually by basically looking at how the object dents, and we can just pick out the constant C. But this in the future we can easily just use a camera to track the deformation. Note that because the vest, the one in the middle on the bottom, it's pretty stiff, meaning that the entire surface kind of moves along with it. When you press it down, you don't see a very clear groove on it. But in the other objects that are softer, you see that there's a pretty clear groove. Oh, I forgot to mention that the color in the images show the amount of surface displacement. To quantitatively see how accurate the prediction is, we also learned models for the line and cylinder probes for comparison in the same fashion as how we learn the point interaction models. Note that we only collected data for the probes when the main axis is aligned with the normal, so we didn't actually rotate the probes in different orientation, which would make the learning process much harder because you have more input dimensions. Our model is able to predict force at a comparable level with uh, the learned models for line and cylinder probes. However, our model is not restricted to a certain shape. It can predict for arbitrary shape and arbitrary orientation and depth. Finally, we show our simulator on a simple planning problem. Here we have rigid box with a piece of lamp in it, and we would like to pack another rigid object into it without exceeding some amount of force. Then we basically do a grid search and move the object down until the force exceeds some force threshold. The heat map is shown on the right. Excluding collision detection time, we can predict force at about 100 Hertz, which is reasonable for a planning problem. So what's next? We have all these simulators. What do we want to do about them? So currently, I'm trying to plan trajectories for a robot traversing granular terrain. So I would want to compute the planned trajectory and control that would maximize some certain performance measures. In the field of trajectory optimization, transcription methods are very popular. It basically turns this planning problem into a nonlinear numerical optimization problem. Solving these kind of problems usually will require gradients of the robot dynamics. And recall what we have for simulating a robot on granular terrain is that we have a convex optimization problem. And to get gradients, we can actually perform a sensitivity analysis on the convex optimization and get the gradients. This is what I'm currently working on, and I don't have results yet, but hopefully in the near future I should be able to get some reasonable results. Um, the Another approach is actually reinforcement learning, where we can throw this simulator into a model-free IL algorithm that basically treats the simulation as a black box, and we might be able to get some reasonable result out of it. I'm also trying to implement this and use it as a baseline for the trajectory optimization. Another venue for future work is actually moving the simulation for the robot on granular terrain from 2D to 3D. This I would we already have some plan for it, but we haven't had the time to work on it. But hopefully in the future I can get around to also extend this to 3D. That should be it for my talk, and thanks everyone for watching. Let me know if there's any questions and concerns, and I'll be happy to answer them.